Okay. Hello everyone, my name is Jean-Michaël. I'm going to talk to you today about graphic advances in ossia score. I work at the Society for Arts and Technology in Montreal as head of technological development. And first I'm going to show you a little bit what is the SAT.
The SAT is a research lab for digital creativity. Technological arts education for ages 7 to 77. A restaurant inspired by a social club for artists and the public. A rooftop patio. And a coffee shop in the heart of downtown. It's also residencies in the field of digital art and innovative artistic creation. A concert venue that hosts both international and emerging Quebec artists. Projection dome dedicated to immersive performances, films, and parties. The SAT is an experience for all.
All right. So, as you can see at the SAT, what we do is art residencies, media arts, etc. In particular, we are very famous for our full dome environment in which we can project movies in 360 and mainly do media art, do art residencies, and any kind of thing that involves both arts and technology. So, in this talk, I'm going to focus mainly in one of the software we developed, which is called ossia score. It will come with a disclaimer. This talk is entirely done in ossia score, so there will be bugs, glitches, crashes, because it's really living on the bleeding edge of the bleeding edge. And yeah, as you can see here, for instance, my slides are just an object here, and I can change like this to go to the next slide and showcase a cute little shader as background with some text. So what's an ossia score? So it's a show control system. So what is a show control system? It's a system that is going to connect the projectors, the sound system, all the intermedia, affordances, light fixtures, etc., that one may find in a show, an art installation, an event, anything where you need to connect multiple kinds of media together. ossia score in particular supports a fair amount of protocols, so standard show control protocols such as OSC, DMX, MIDI, OSC query, MQTT, etc. There is quite a long list, so here we can see a bit all the protocols that are supported, including some weird stuff like GPS, for instance, if you need to do portable installations, or if you are on a Linux machine, you can use EVDEF to get raw access to your hardware feature of your laptop. So here I can access to my power button, which of course is useless because as soon as I press it, the computer goes down. What else is an ossia score? It's also an audio and video real-time visual data flow graph. So for instance, you may know Pure Data, MaximSP, TouchDesigner, this kind of environment, combined with a timeline which supports interactive cues. So data flow graph, basically, if you look at this, you're going to see different nodes. So each of these nodes are a single shader that are going to run one after each other. So here, for instance, I can look at the code of my shader and go and edit it in a live coding fashion. And in a way, ossia tries to be a really live coding friendly environment. It works on Windows, macOS, Linux, and also embedded systems, so such as Raspberry Pi, and we will try to be really inclusive of which hardware ossia runs on. In terms of graphics backend, in particular, what interests us today, it can use Vulkan, Direct3D, Metal, OpenGL, depending on your platform. And it acts as a bridge between many environments, platforms, protocols. Really, it's defined by its huge amount of integrations, and hopefully there will be more to come. But for instance, you can use directly FMPEG, GStreamer, VST plugins for audio. So it comes mostly from the audio field. So VST, LV2, VST3, Clap, GSFX, shaders, etc., etc. and supports, again, thanks to FMPEG, a vast amount of audio and video formats for live media with hardware decoding and scrubbing. So for instance, thanks to the FMPEG people, we get Vulkan video, we get ProRes support, HAP, DXV, etc. And the whole graphics pipeline is GPU only. So what does it mean to have this kind of features? For instance, what does it bring us? I will open another example. So here, for instance, so here we have one instance of a video file that I'm going to be able to grab to. So here I'm going to be able to move my audio file live. So this video file, sorry. So this video file is a minute and 30 seconds, and it's also 150 gigabytes on my hard disk, and it's roughly 1 byte per second. Yeah, 1 minute per second. And you can scrub in it really live without any delay latency. So it's the kind of feature that we are really trying to work on, so that artists can basically not feel blocked just because they will have a lower performing computer. And it's been used in award-winning art installations and performances all around the world. So yeah. So next slide. Yeah. So what happened recently in the Ossia score world, and this makes me think that I didn't open the tab. Most important recent milestone, stream diffusion support. So what's stream diffusion? It's a system that allows to do real-time inference of AI models such as Stable Diffusion 1.5 XL Turbo. We ported this to C++ and we embedded it in Ossia, and we're going to embed it in other software soon. So just to show a few examples of what this looks like. Basically, you can take some input images and turn them into real-time AI visuals with this tool. Some of the AI models, for instance, Stable Diffusion Turbo can run at more than 60 FPS, so you can get very, very fluid performance if you have a fast enough input camera or shaders. And even smaller models can run at really crazy speeds. For instance, Stable Diffusion XS more than 600 FPS, which is more than enough for any reasonable requirement. Full DOM immersive rendering pipeline, of course, since we work at the SAT, which has a full DOM environment, we need to be able to produce visuals for this DOM and allow artists to use it efficiently without relying on proprietary tools. HDR support, so we can, the whole of the software is compatible with HDR, both from ingestion of input media. It has tone mapping operators. It has everything that is needed to go from a high log, different color spaces, etc. All the tools are here, and full Qt Quick integration. So what does this mean? So Ossia is built with the Qt framework in Qt 6. And for instance, this presentation system is actually just an object that you can also live code here in Qt. So of course, live coding your own presentation system while you're doing the presentation is not a great idea, but you get the gist. Here I can have this little Qt window, and I think it's this slide, and I can say hola, and the slides change, and that's it. So what else? Video mapping. Okay, that's a big one. I'll make a new document for this. And okay, video mapping is when you have projectors and you want to basically project shapes, etc., on this projector. So there are two dimensions to this problem. First dimension, if you have only one projector, how does that look? Let's see right now. Okay, I will add a window and I will add a mapper object. So this is a bit crash course how you use a software like Ossia. So here I have my video mapper object. I will add some, I don't know, cubes. I don't know. Yeah, something like that. So I will just add this shader here to my video mapper, and my video mapper will output to a window, and I hit play, and it will crash because I'm being reckless. Okay. here. So here I'm going to be able to add a few different shapes to video map. So here I'm going to be able to tier and stretch the video and turn it extra and duplicate it and draw it in a freehand way or with polygons, etc. And add stuff such as, for instance, edge blending so that we can blend our video inputs and outputs in each other. So this is one part of the problem. This can be used for architectural mapping. So here, for instance, I could say, okay, actually, you're going to act as a mask. And then there is the second part of the problem, which is how do you do when you have multiple projectors? So here we also have tools for this. So we can say, okay, I actually have 2 free viewports that are going to be different parts of a big, large texture, and each is going to view inside this texture. And again, we're going to be able to stretch and adjust things so that we can get proper blending when we have to put 4 projectors next to each other. So that's it for video mapping. I'll start again to go back to the slides. Yes, so we're here, slide up, 1, 2, 3, 4. No, 3. We're still on slide 3. Here we go. So what else? And streaming, export, recording. So there's now deep GStreamer and FMPEG integration, which allows, for instance, cool stuff such as saying, oh, I want to ingest, let's say, WebRTC, RTP, etc. I want to export using NVENC. Any kind of GStreamer pipeline can be used. Likewise, for FMPEG, we can basically pass any FMPEG compatible option and preset and make our own pipelines to stream audio, video, etc. over the network. And then there's what we are doing right now, in-progress features. So for the longest time, Ossia's video pipeline was only about applying filters, shaders to videos, which already opens a lot of use cases. But at some point, someone comes up and says, oh, actually, I want to also be able to just move an object around, a 3D object, and I want to rotate around it. And then I want to add lights, and I want my light to work on all my objects. And when you are here, when you need one light to apply on 2 objects, then you have a scene. And the big question is, how do you turn something which is hybrid between timeline and data flow into a scene graph, which is more akin to a game engine? And that's what we're going to see in the rest of this presentation. And a few other points that I want to say that are important and that always accept help is we need presets, demos, examples, etc. One thing which is very relevant for us Linux folks is pipewire video inputs, so that we can have something equivalent to Spout and Syphon on Linux, which doesn't copy buffers, but just directly shares video memory, for instance, between different software, OBS, etc. And Wayland advocacy, because, for instance, what I showed with video mapping, right now it's something that really depends on X11 features and doesn't work with Wayland. And finally, next steps are modern rendering pipelines, so ray tracing, etc. Last year, we had a GSOC Google Summer of Code student, so student paid by Google for a few months, who did a prototype of how could we embed a ray tracing pipeline that really leverages the GPU into a Ossia Core implementation. This was successful, so now we have to turn this prototype into a concrete implementation. And yeah, so in terms of shading, Ossia leverages ISF, interactive shader formats, which was developed by Vidvox quite a few years ago and is at the core of VDMX, and also some other software such as Resolume, I think Coolab, use it, etc. ISF only works for full screen quad shading, so basically applying a filter, generating something entirely with sign distance fields, etc. So the first thing we did was add a fair amount of extensions to ISF so that we could go much further in terms of what are the applications of this shader. So here, for instance, what you're seeing behind is a cube that is being generated by a compute shader and then being rendered as a 3D texture by a complete render pipeline, which is purely based on ISF shaders, extended ISF shaders. So we did stuff such as 3D texture support, depth red, depth right, so that we can apply post-processing effects that will depend on depth, etc. Multi-render target, all the kind of features that you need when you make not just video filters, but an actual 3D pipeline. And I will just make a quick demo of how this looks like. So for instance, first example, you may know this one. Which actually may be broken now. Let's see. Yes, no, it's still working. So here you may recognize the famous Sponza scene. So here I can move light around, etc. And it's not that slow. Yeah, here. And basically do proper 3D rendering. So here we really have a proper 3D scene where we can move around, rotate things, etc. We can have environment maps, etc., etc. And this is our scene graph. So here, for instance, the entire amount of objects we have is a light, our GLTF model, and then one object to turn our scene into some visuals, and then a PBR shader. Then with the ISF extensions we have, we can go a bit further and add, for instance, some depth effects. So here, for instance, there's our same PBR pipeline. And then we do something that, for instance, Touch Designer cannot do, which is process the depth in multiple successive shaders. So here I can have multiple depth of field effects, which each with different focus, so that we can make various kind of depth-based effects. And again, this is all code that is just ISF shader embedded directly in the system. So if I go back to my slides, where are we? Here, so shading models, and then I think I don't have too much time left. So the big extension we did to ISF was adding support for compute shaders, so that we could, for instance, process buffers, geometries, etc., directly on the GPU. So there's a few examples of this on the website. So here, this is a very simple example of taking a shape and just generating points that match it. I will do another example, which is this one. And here, for instance, so this is struggling a bit with the HDMI output, but we're having a few tens of millions of particles generated by a compute shader on each frame. And then we just render them. It's pretty just random stuff. And yeah, that's the kind of things that we can work with real geometry and then turn this geometry into mesh that then become part of the scene system. So, yep. And then, and one thing is we can do all kinds of buffer feedback effects, so systems such as reaction diffusion, etc. Pass buffers that turn geometry into add attributes to geometry, etc., etc. And then feedback to the beginning, so that we can have classic particle effects and this kind of things. Then the next step was extending ISF with a way to not just render a quad, but render arbitrary kind of geometries. So we added some features to the ISF JSON so that you can specify attributes, additional buffers, etc. And this really opens a lot of doors, because with this, the entire rendering pipeline is actually just a preset, and the software doesn't ship for instance, PBR shader and a PBR, let's say, pipeline. It's just all built in the user's document through end user presets. So if someone wants to come up with a completely different rendering pipeline, they can. How would such a different rendering pipeline look like? Let's look at some examples. So I think it's this one. Let's see. No, it's not this one. That's what I get for doing live demos. Geometry feedback. Yeah. So here, this is a very simple case of feedback. We have one shader that is going to be generating some attributes, so position, color, and sprite size. And then we're going to have one render shader that expects this and then turn it through a fragment, vertex and fragment shader into a classic sphere splatting algorithm to turn just a point into a proper visual. And this is one kind of rendering, but again, this is just a preset of the software and not something that will be built into it. So anyone can and should come up with their own shaders and rendering pipelines. For instance, right now the trend is at spectral rendering, and definitely it's something we want to explore to see how we could have this kind of new rendering techniques implemented. So here, for instance, another one at the background of this slide, voxel rendering. So we can take, for instance, voxel meshes from, how is it called? Magica Voxel, and create a rendering pipeline specially made for turning voxels into cubes, etc., etc. And I'm out of time. So very quickly, I will just end and finish. Thanks for your attention. All the tools we develop at the SAT are free and open source, so they can all be downloaded, and workshop Saturday at 1:20.
So do we have questions? No? We want to have it.
I think for internet, it's important to...
I've tried to use Wayland in production for a few things, and it's been kind of bumpy, and it looks like it's been similarly bumpy for you. And obviously people have to ride it to get it better. What are the things that make it worthwhile for you to take the lumps with the sugar with Wayland?
To take the what? Sorry.
What are the Wayland features that make it worthwhile for you to be on the bleeding edge and to risk the occasional crash?
I will say it's just that, so here, for instance, GLTF is not in any released version yet. So this is kind of thing that, has been in development for the last 6 months, but is still hiding in a branch. But I think for today, I really want to show this. The last stable release, for instance, has complete shaders, has all the shader pipeline. It doesn't have any of the more advanced 3D model loading. And in terms of platform, I'm an Arch Linux user, so I like taking the risks and I like the bleeding edge. And it actually works better than, Ubuntu or anything else on this machine, but really it's more of a hardware problem than...
Okay, cool. Thank you very much. We may have time for another quick question, but Jan should already start to switch over. So if anyone, Abe?
I was wondering, it seems to do so many things, like how to learn, how to get into it.
How to get into it. So right now at the SAT, we're trying to make a complete tutorial series. There are tutorials, there's documentation online, there's a whole documentation website for people like me who like text, and for people not like me who like video. There's old videos that are not entirely up to date, so they can still be followed, but we really want to make a complete new curriculum this year to give all the information. So yeah. And the Discord is also a helpful place. There's social media, there's people asking questions. So yeah.